We're going to be tackling a topic that's pretty mind-bending, even by our standards.
It's a good one.
It is quantum tunneling. And judging from the sources you send us, you're already a bit familiar with the concept.
Right.
But we're going to go deeper. So what specifically about quantum tunneling are you most curious to explore today?
Well, I think what really gets me is that it just seems to defy our everyday experience.
Yeah, totally.
Like, we're so used to objects behaving predictably,
Right.
like a ball rolling down a hill.
Yeah.
But with quantum tunneling, it's as if that ball could just suddenly pass right through the hill.
Yeah. No, it's like the rules we used to just kind of break down.
Exactly.
So help us understand how that tunneling part actually happens. Where do we even begin with that?
Okay, so in quantum mechanics, we have to shift our thinking a bit.
Okay.
We have to start thinking about particles not just as these tiny points,
Mm.
but also as having wave-like properties.
Okay, so they're not like physically transforming into waves, right?
Right. It's not a literal transformation.
Yeah.
It's more that their behavior is described by something called a wave function.
Oh, okay.
And this wave function basically represents the probability of finding that particle at a certain location.
So instead of picturing a solid ball, we should be thinking of something more like a ripple spreading out.
Exactly. A ripple or a wave, that's a good way to visualize it.
Okay, I'm with you so far, but how does that explain going through a barrier? Like, how's that wave getting to the other side?
Right. So here's the key. That wave function, it doesn't just abruptly stop at the barrier.
Okay.
It actually extends into the barrier, but it starts to decay exponentially as it does.
Oh, interesting.
So what that means is there's still a chance, even if it's really tiny, that the particle could be found on the other side.
So it's almost like it's leaking through in a way.
Yeah, that's a good way to put it.
And then we might suddenly detect it on the other side as if it tunneled.
Exactly. And it's one of those things that really highlights how strange quantum mechanics can be.
Right.
It's not like the particle is physically burrowing or anything.
Wow.
It's more about this probability wave and the chance of finding it in different places.
Okay, so there's an inherent randomness to it, but it's not just pure chaos. Right.
Right. There's an underlying order to this randomness. And that's where the Schrödinger equation comes in.
Ah, yes, the famous Schrödinger equation. Your sources definitely emphasize that one.
Yeah.
But instead of just throwing a bunch of variables at us, can you help us understand what that equation actually tells us about this whole tunneling process?
Sure. Think of the Schrödinger equation as a way to describe the energy landscape
Okay.
that our particle is moving through.
Okay.
It takes into account things like the particle's energy, the height of that potential barrier it's facing, the particle's mass, all these factors.
So it's basically a mathematical way to describe that ball and hill analogy we were talking about.
Exactly. It helps us figure out how likely it is that our ball is going to tunnel through that hill based on all those different factors.
I like it. So it's like, even if you don't think you have enough energy, there's still a chance you can sneak through using these quantum rules.
Precisely. And that's one of the things that makes quantum tunneling so fascinating.
It's so cool. That, not all hills are created equal.
Right.
And your sources mentioned something called the WKB approximation. What's that all about?
Yeah, so the WKB approximation comes in handy when we're dealing with potential barriers that are a bit more complicated than a simple hill.
Okay.
Imagine a barrier that's not a smooth rectangular wall, but it has curves
Oh, okay.
and varying heights.
Like a roller coaster almost.
Yeah, more like a roller coaster track.
Okay.
And the WKB approximation gives us a way to calculate those tunneling probabilities, even in those more complex scenarios.
So it helps us navigate those twists and turns, even if the barrier isn't a perfect, neat hill.
Exactly. It allows us to make sense of tunneling in those situations.
Gotcha. So we've talked about the theory, but let's bring this back down to earth a bit. Where do we actually see quantum tunneling in action?
Oh, well, you might be surprised to learn that it's happening all around us, even in the most unexpected places.
Like where?
Like, for example, in the sun.
Wait, the sun? That giant ball of fire relies on quantum tunneling.
Absolutely. It's essential for the nuclear fusion that powers the sun.
Okay, now you have to explain that one. How does quantum tunneling work in the sun?
So deep inside the sun, you have protons constantly trying to fuse together to form helium.
Right.
And this releases a tremendous amount of energy.
It's like a giant nuclear reactor up there, right?
It is. But there's a problem. Protons are all positively charged.
Okay.
So naturally, they repel each other.
Right, like trying to push the same poles of two magnets together.
Exactly. So how do they overcome that repulsion to fuse?
Yeah, that's a good question.
Well, that's where quantum tunneling comes in. The protons actually don't have enough energy to overcome that repulsion classically.
Hmm.
But thanks to quantum tunneling, there's a small chance
Yeah.
that they can tunnel through that repulsive barrier and fuse together.
So every time I feel the warmth of the sun on my skin, I'm literally experiencing the effects of quantum tunneling.
You got it.
Mind-blowing.
But the sun is just one example, right? What other real-world impacts does quantum tunneling have?
Well, it plays a role in all sorts of technologies. For example, in tunnel diodes,
Hmm.
they utilize tunneling to achieve negative resistance, which is important for high-speed electronics.
Interesting.
And then there are Josephson junctions,
Okay.
which exploit the Josephson effect,
Mm-hmm.
which is another manifestation of tunneling,
Mm-hmm.
to create supercurrents that can flow through barriers.
So these are used in things like highly sensitive detectors, right?
Yeah, and even in the development of quantum computers.
Wow. Okay. So we're seeing how this very strange, very small-scale phenomenon
Right.
is actually having a huge impact on technology that we use every day. It really highlights how the quantum world, despite being so bizarre,
Yeah.
is actually intimately connected to our everyday reality.
Okay, so we've established quantum tunneling is happening all around us, even in the sun.
Indeed.
But I'm particularly intrigued by its potential in, quantum computing.
Oh, yeah.
Like, what's the connection there? How does tunneling fit into all that?
That's a great question and one we can definitely dive into more deeply. But maybe we should save that for part 2.
Yeah, that sounds like a great place to pick up next time. Okay, so we're back and ready to delve deeper into the world of quantum tunneling and its role in quantum computing.
Sounds good to me.
Now, I have to admit, I find quantum computers pretty mind-boggling.
Hmm.
Can you give us a quick recap on how they work and where tunneling fits into the picture?
Sure. So, traditional computers use bits, which can be either a 0 or a 1.
Right, like an on or off switch.
Exactly. But quantum computers use qubits, and these are kind of like super bits.
Super bits, okay.
Because they can be in a superposition, which means they can be both 0 and 1 at the same time.
Whoa, okay, so that's already way more complex than our everyday computers.
Right. It's a whole different ballgame.
Yeah, so it's not just that they're faster, it's that they process information in a fundamentally different way.
Precisely. And that's where quantum tunneling becomes so important.
Okay, I'm listening.
It basically allows these qubits to interact with each other in ways that classical bits just can't.
Oh, interesting. So is it kind of like a quantum communication between these qubits?
It's like they have a secret language.
I like that.
And this communication is what gives quantum computers their real power.
So we're talking about unlocking like a whole new level of computing power here.
Exactly. We're talking about solving problems that would take classical computers, billions of years.
Okay, so what kind of problems are we talking about? Give us some examples.
Sure, think about simulating complex molecules. This could revolutionize drug discovery or materials science.
Yeah, okay, I see the potential there.
Or optimization problems,
Yeah.
like finding the best routes for deliveries or optimizing financial portfolios.
So these are tasks that would just overwhelm even the most powerful classical computers, right?
Absolutely. There were just too many possibilities for them to handle efficiently.
Okay, so it all sounds amazing, but how close are we really to having practical quantum computers?
Well, there are still some major hurdles to overcome.
Like what?
One of the biggest is maintaining the coherence of these qubits.
Coherence.
Yeah, it means keeping them in that delicate superposition state.
Right, because we were saying they could be both 0 and 1 at the same time.
Exactly. But they're incredibly sensitive to any kind of environmental noise.
Okay, so any disturbance could basically knock them out of that superposition.
Yeah, it's like trying to build a house of cards in a windstorm.
Oh, I like that analogy.
And when that happens, we get errors in our calculations.
So researchers are working on ways to make these qubits more robust, right?
Exactly. They're also developing error correction codes specifically for quantum computers.
Okay, so it sounds like there's a lot of work still to be done.
Definitely. But the potential payoff is huge.
For sure. Now, you mentioned earlier that quantum tunneling could also pose a threat to our current encryption methods.
Right.
Can you explain how that works?
Sure. A lot of our current encryption relies on mathematical problems that are very difficult for classical computers to solve.
Like factoring really large numbers.
Exactly. But a powerful quantum computer could potentially crack these codes in a fraction of the time.
Oh, so it's like a security nightmare waiting to happen.
It's a real concern. It could put online transactions, communications, all sorts of sensitive data at risk.
Okay, so are we just doomed then? Is there anything we can do?
Well, thankfully, researchers are already working on quantum-resistant cryptography.
Quantum resistant, okay.
Yeah, these are methods designed to be secure even against attacks from quantum computers.
So it's like an arms race, essentially.
You could say that. As we develop more powerful technology,
Right.
we also need to develop stronger safeguards.
That makes sense. It's amazing how this tiny quantum phenomenon is having such a huge impact on the world.
I know, it's fascinating to think about.
Okay, so we've seen how quantum tunneling is essential for the sun and how it could revolutionize computing,
Mm-hmm.
but I still have to ask,
Mm.
could something large, like a baseball, ever tunnel through a wall?
Okay, let's talk about that.
So could a baseball magically teleport to the other side of a wall? Is that something we might see someday?
Well, theoretically, even large objects have a wave function.
Okay.
So there's a non-zero probability, however tiny, that they'd tunnel. But the probability drops off incredibly fast as the object gets bigger and as the barrier gets wider. So for something like a baseball or a person tunneling through a wall,
Right.
it's just astronomically unlikely, basically impossible for all practical purposes.
Okay, so my dreams of being a superhero are officially busted.
Yeah.
But still, the fact that it's even theoretically possible, that's pretty wild. It makes you wonder about the barrier itself, though.
Yep.
Like, does it matter what the barrier is made of? Would an electron have a harder time tunneling through a wall of lead versus, say, a wall of cheese?
That's a great question. It really gets to the heart of what we mean by a barrier in quantum mechanics.
Okay.
It's not so much about the physical material itself,
Mm-hmm.
but more about the energy landscape that the particle encounters.
So it's not about the stuff of the barrier, but the energy it represents.
Exactly. Think of it like a landscape with hills and valleys.
Okay.
The hills represent regions of high potential energy, and the valleys represent low potential energy.
Okay, I see the analogy.
So a particle needs energy to climb a hill,
Right.
but it can easily roll down into a valley.
Okay, so how does that apply to tunneling?
Well, in quantum tunneling, the barrier is essentially a hill in this energy landscape.
Got it.
The particle might not have enough energy to climb over it, but its wave function can still extend into and through the hill, giving it a chance to tunnel.
So whether that hill is made of lead or cheese doesn't really matter. It's more about the height and shape of the hill itself.
Precisely. The material might influence the shape of the energy landscape, but ultimately it's that energy difference that's key.
So an electron might have a totally different experience depending on the energy, not just what the barrier is made of.
Exactly. It really highlights how quantum tunneling makes us rethink our everyday ideas about barriers.
It's not about being solid or impenetrable. It's about energy and probability.
Right. It's a whole different way of looking at things.
It's incredible how something so abstract can have such a big impact on how we understand the universe
I know, right.
and on these cutting-edge technologies we're developing.
Absolutely. And the more we learn about the quantum world, the more we realize how much we still don't know.
It's a constant source of mystery and wonder, that's for sure.
It really is. Always pushing the boundaries of what we thought was possible.
Well, this has been an amazing journey. We've explored quantum tunneling from the heart of the sun to the frontiers of quantum computing. And I think it's safe to say we've all had our minds blown a few times along the way.
More than a few times, I'd say.
To our listener, thank you so much for joining us on this deep dive into quantum tunneling.
Yes, thank you.
We hope you've gained some new insights and maybe even a renewed sense of awe at the strangeness of the quantum world.
And remember, even if you can't walk through walls,
Right.
there's a tiny quantum part of you that just might be able to.
Until next time, keep questioning, keep exploring, and keep your mind open to the endless possibilities of the universe.